Okay, I'm going to take a second to talk a little more about these recursively defined sequences and or recurrence relations, if you want to call them that. And what I'd like to do is actually show a little bit of code. This isn't something I do typically, but actually I'd like to look at the, you can always look at the factorial function. We can define the factorial function recursively. It can also be defined iteratively. So if you give it a number, right, you can just multiply 1 times 2 times 3 times 4 all the way up, right? So why don't I actually just define a function here in Python. I'm just using Python. I'm just going to do scripting in the console here. So I'm going to define a function. I'm going to call it fact. We'll call it factit, right? So this is going to be the iterative factorial function. I'm going to pass in a value in, and then what I'm going to do is I'm going to have like a I'm going to set the total equal to 0 for I in range. We'll say in. Let's see, I'm going to do for I in range in total equal, and here I'm actually going to have to do I plus 1 times the total. Actually, you know what? I need to make the total equal to 1. Okay. And then here at the and then at the end, what we want to do is just return the total. We could try something like let's see, I can try something like maybe 3, right? So we should get 6. Right. I could do 5, right? We should get 120. So, right, all I'm doing here is I'm doing an iterative process of multiplication, right? So here I'm starting from the bottom and saying that I do 1 times 2 times 3 times 4 times 5. Right, so then I'm doing all the multiplication and sort of like totaling it all up. There's another way we can actually define this. So I can define a function. I'll call it recur, right? We can define it cursively for a value in, right? If in equals 0, right? Return 1, right? Else return, we're going to do in times, and then here is the kind of interesting thing. I'm going to call the function on itself inside itself, right? With, I'm going to pass in the n minus 1 argument. Now, hopefully you see that I have to put in non-negative integer values, right? But that's kind of what the factorial function does anyway. So notice I can put 3 in, right? I get 6. And if I put 5 in, I also get 120. Right? So, there's other kind of interesting recursively defined sequences. I talked about the Fibonacci, right? I can define a function, right? Fibonacci, or I can get we can get sort of like the nth Fibonacci number starting at 0. So if I wanted to sort of like, if we're imagining that the first number that it gives me is the 0th Fibonacci number, right? So what I can do here is I'm actually going to need two things, right? So I'll define the Fibonacci to be if n equals 0, all right, I want to return 1, else if n equals 1, right, here I want to return 1 as well, and then, right, what's the general case, right? So I kind of have the two sort of base, right, at 0 and at 1, right, those are my initial condition things, and then now the general case, so what I want to do is I want to return fib, right, in -1 plus fib, right, in -2, right, and so there we go, right, so now if I call fib, so if I do a 0 or a 1, I should get 1, so if I put 0 in, right, it gets 1. If I put 2 in, I should get the number 2, right, because it's the sum of the first two numbers there. Now if I put in something like the fifth, what's the fifth Fibonacci number? That's 8, right? If we think about that, what it's doing is it's creating these called stack frames, and basically it's kind of like calling itself and saying, well, I don't know what this is, but I do know that whatever I return is the n-1 plus the n-2, right? And so then it goes, okay, well, I don't know what that is, but I do know that n-1 for Fibonacci is actually Fibonacci of n-2 plus Fibonacci of n-3, and then Fibonacci of n-2, what is that? Well, that's a Fibonacci of n-3, it's Fibonacci of n-4, right, and so on, right? So we get this sort of like everything built up, and you get down to the very lowest numbers, when n is 0 and n is 1, then it actually knows what to return, right? It returns 1, and then it sort of builds itself back up. So rather than having it, when we were doing stuff iteratively, what we were doing is we were totaling things up every time, right? And so the example I gave in 5.4 for this sequence, we can actually define that. I'll call it this function. I can pass in the some integer value in. And I'm not doing error checking on this, so I know what numbers I'm going to put into it. If you were going to use this as like a general thing, you'd want to make sure that people are putting in integer values and that the integer values are non-negative integer values, or however you're defining your function, whatever things work in your function. So in this case, if we remember sort of the A0 term was 1, the A1 term is 5, and then we have the general case, right? What does it look like? So here I'm just going to write if, right, n equal 0. Right? What do I want to do? Well, I want to return the value 1. If n is 1, right? What do I want to do? Well, I want to return 5. Else. Now here is where we write the sort of like the definition. So it's the n-1 term, right, plus 2 times the n-2 term. Right? Let's see what the problem is there. Okay. So if I go in, like I can try term number 2, right? And when in is 2. So I want the A2 term. I should get 7. I hope it gives me 7. Right? It gives me 7. Oh, 3, right? So there's 17. And one thing that's kind of interesting about this, right? We found a closed form of this, and it actually turned out that with the closed form, it was either 1 more or 1 less than a power of 2, right? Which is that's kind of a neat thing there. So let's see. I'm just going to have the function. I'm going to call it right. Why am I doing this? Well, because I don't really want to plus, right? So I want plus -1, the power of, and this is n plus 1 again. My goodness, what is happening? -1, the power of n plus 1. So I just did this because I don't want to don't have to rewrite this a bunch of times. So for this, I should get 17, I hope, if I did it right. Yeah. So now, notice I could have my recursive function. I could put in the number like, well, if I put in a large number like 30, you see it took like a second for it to do that. This one will actually return much faster. So let me try 100. This might, we'll see if this works. Might take a second. Hopefully it doesn't crash. And my computer is really thinking now. Let's see. Still going. I may have to stop it if it doesn't spit out an answer in just a minute. So the reason this is taking so long is because you notice what it's having to do is it's actually having to call itself. It's having to call this function many times, right? Allocate that memory appropriately, and then build itself back up. So I'm just going to stop this here. Okay, well, interesting. It has decided not to stop itself. Well, that's obviously not ideal. So, well, what have I done? I've apparently I've broken its computer brain, so it doesn't know what to do right now. Let's see if I can just close this console and open a new one. And it's decided not to do that. Okay, well, huh? I have to restart everything. Okay, it started a new one. I don't think I probably have that. So anyways, you saw how long that was taking. And I doubt that it has saved that since I closed the console, but we could always try. Yeah, it doesn't have that. It's not defined. So let's define this the closed form solution value. So this is a reason sometimes you might want something to be in a closed form that, maybe it's very large. And what I'll say is Python is actually not the best language to use for recursion. So, if I was writing it in C or C++ or Java or some other language can handle recursion a little bit better. So let's see. Remember, this was 2 to the power of n plus 1, right? And then I've got negative 1, and then this is going to be to the power of, again, n plus 1, right? So that's what we want to return. So here, let's see what happens when I do that. Well, there's the number, right? And notice it returned it in just a second. Why was I able to do it so quickly? Well, it's because that this closed form thing is not dependent on calling itself multiple times and creating this this large set of stack frames, right? Hundreds or thousands of stack frames, allocating the memory appropriately and doing that. So it's much, much faster to do it this way if you can find it, right? And so sometimes that's a reason we would actually want that. And if you remember in the video for 5.4, we actually proved this using strong induction that this closed form is true always, right? So it doesn't matter what value of n I put in, it's always going to be correct. And I guess that's it for right now. Thanks.